Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna, for introducing the session. A very good day to everyone. Thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jia Ying from ITU, the International Telecommunication Union. Today, we are having another exciting webinar titled Wireless Foundation Model Empowers Synesthesia of Machines System Design. This webinar serves as an introductory webinar to the relevant challenge, which aims to fine-tune the wireless foundation model to finish channel estimation, line of sight and non-line of sight classification, and vision-aided wireless localization. In the webinar, our speakers will explain the tasks to be accomplished by the participants, evaluation methods, logistical details, and prizes for the winners. But before officially kicking off the session, I would like to introduce our esteemed speakers, Boxun Liu and Professor Xuesong Cai. Boxun Liu, PhD student at Peking University. His current research interests include AI-empowered wireless system design and integrated sensing and communication. Professor Cai is the associate professor at the Peking University. His research interests include multi-modal intelligent radio channel characterization, high-resolution parameter estimation, over-the-air testing, resource optimization, and radio-based localization for 5G and beyond 5G wireless systems. And my colleague Vishnu, who will be taking care of the Q&A session. Now, without further ado, I would like to pass the baton to Boxun. Boxun, the floor is yours.
Okay, thank you, Jia Ying. I will share my screen.
We can see your screen.
Oh, okay. Hello, everyone. It's a great honor to join today's AI for Good webinar, the wireless foundation model empowers SoM system design. My name is Boxun Liu, and I'm a PhD student from Peking University. Today, I will introduce our ongoing competition, the Synesthesia of Machines SoM Challenge 2025. My partner speaker is Professor Cai, and we are both from the Pervasive Connectivity and Network Intelligence PCI group from Peking University. We would also like to sincerely thank the Huawei for sponsoring this competition. And in this webinar, I will first introduce background, including the concept of SoM and WiFo, and I will introduce problem statements and the evaluation criteria. Next, I will introduce the datasets and the baselines, and finally, I will introduce the computation procedure. Firstly, the integration of communication with intelligence and sensing is a key development trend for 6G. Against this background, our group has proposed the concept of Synesthesia of Machines, SoM, which is a novel paradigm for AI-native intelligent multimodal sensing and communication integration. And SoM aim to explore the reciprocal mechanisms between the wireless communications and multimodal sensing information. The main research topics of SoM can be summarized into the following 5 aspects. And today, our competition is primarily related to the third aspect, SoM enhanced transceiver design. Specifically, it aims to achieve an AI-native multimodal sensing-aided wireless physical layer design. Existing SoM enhanced transceiver design rely on task-specific AI models and faces the following challenges, including the poor performance, the limited generalization, and the disjoint design. And recently, wireless foundation model had been explored as a promising and new paradigm for wireless physical design. Specifically, the wireless foundation model is pre-trained on a broad wireless data, typically at scale, using the self-supervision and adaptable to a wide range of wireless tasks through few-shot or even zero-shot learning, and their performance can outperform the task-specific models. And our previous work developed WiFo, the first wireless foundation model for channel prediction. It's the first wireless foundation model to address the time domain and the frequency domain prediction task in one for all manner, handling diverse CSI distributions and system configurations. It is pre-trained on massive heterogeneously CSI dataset. The WiFo can be directly utilized for channel prediction without any fine-tuning. It is built upon a masked autoencoder network structures, and it consists of following 4 parts. We design self-supervised pre-training tasks for WiFo based on mask reconstructions, including the time domain, frequency domain, and random mask reconstruction. During the pre-training, we mask the CSI along time dimension, frequency dimension, or randomly to enhance the multi-domain channel prediction capability. After pre-training, WiFo poses a general CSI reconstruction capability, which can be directly applied to the time domain or frequency domain channel prediction. We have conducted intensive simulation to verify the WiFo can simultaneously learn from 16 heterogeneous CSI datasets. Moreover, WiFo demonstrates remarkable zero-shot channel prediction performance, even surpassing the full-shot performance of task-specific AM baselines. Nevertheless, as a wireless foundation model, we believe WiFo can enable more wireless tasks via CSI representation learning. Therefore, in this challenge, we aim to fully explore WiFo's potential to empower CSI-related downstream tasks through fine-tuning. We select 3 representative CSI-related SoM tasks, including the channel estimation, loss-unloss classification, and vision-aided wireless localization. And in this challenge, we use the base version of WiFo. It has 21.6 million parameters. Then I will introduce the problem statement and the evaluation criteria. The first task is channel estimation, which is important to obtaining the CSI in wireless communication systems. It aims to recover the complete CSI from sparsely placed pilot signals in the time-frequency resource grid. The task input is a CSI at the pilot positions of the time-frequency resource block, and the task output is a complete CSI. And we use the NMSE as a metric. The second task is loss-unloss scenario classification, which is crucial for selecting appropriate wireless communication strategies. Its objective is to determine whether the environment is a loss scenario or an unloss scenario based on the given CSI samples. The task input is a two-dimensional CSI sample, and the task output is a scenario label. We adopt the F1 score to measure the classification accuracy. And the third task is a vision-aided wireless localization. Its goal is to perform user localization by jointly exploring CSI and the RGB images captured at the base station set. Therefore, the task input consists of both the CSI and the image collected at the same time, and the task output is the user's location. And we use the MAE as a metric. Since the goal of our computation is to achieve efficient enablement of the physical layer tasks based on the WiFo, therefore, the evaluation scores comprehensively consider the performance on various downstream tasks, as well as practical deployment overhead of this model. Firstly, for the 3 tasks, we provide task-specific score and scoring methods to ensure that each score lies in the range from 0 to 1. And for the model practically score, we compute it based on the number of fine-tuning parameters rather than the total number of model parameters. And the final score is then obtained by combining the task-specific scores with the model practically score in order to encourage solutions with lower training cost. Then I will introduce the datasets and our baselines. Although WiFo has already been pre-trained, we allow the participants to further pre-train the WiFo on the unlabeled CSI dataset to enhance its generalization capability. Then for the downstream fine-tuning, the dataset is can be downloaded from this link. For each task, we provide a training dataset, a validation dataset, a public testing set, and a hidden challenge testing set. The training dataset and the validation dataset are labeled and are used for fine-tuning. The public test set is used for evaluation during the development phase. That is, participants upload their inference results to the system and receive their scores in real time. The hidden challenge testing set is reserved for the final test phase, where the organizers will perform manual evaluation based on the submitted code rather than the submitted results. The pre-trained weights of WiFo base and a roundabout baseline are also provided, and we strongly encourage the participants to carefully study the baseline codes, which include the training scripts for the 3 tasks, the instructions to reproduce the scores, and the expected submission format. And you may also refer to some of our previous code, including the inference codes of WiFo and other fine-tuning codes. It is important to note that it is strictly forbidden to use any external datasets for fine-tuning on the downstream tasks. Here I will introduce our provided baseline, which we are open sourcing for the very first time. The baseline including the 3 tasks. For task 1, we will first interpolate to obtain the raw CSI and then use the WiFo encoder-decoder structure to reconstruct the estimated CSI. And for task 2, we use the WiFo encoder to extract the channel representations from the raw CSI and then apply the linear head to obtain the prediction. And for task 3, we extract the channel features with WiFo encoder and combine them with RGB features obtained by RGB encoder and predict the final position. To achieve a higher score, you can optimize a fine-tuning strategy. You can optimize the data pre-processing pipeline. You can tune the network hyperparameters, or just be lucky enough. Finally, I will introduce the computation procedure. In the first phase, the participants submit their inference results on the public testing sets, and the system automatically scores them and updates the leaderboard in real time. It is noted that only the top 5 teams will advance to the next phase. In the second phase, these top 5 teams have 10 days to provide materials for verification and reproducibility, and they will provide some materials such as roundabout inference code, the model weights, the documentation, and the instructions. And in the third phase, our organizers will manually compute the score of the participants and announce the final ranking 5 days later. We also have set up a forum for communication and question and answer. The link is here. And we encourage all participants to ask questions on this forum to avoid duplicated inquiries. And our computation provides a total price of 4,000 CHF, which 2,219 CHF for the first place, the 1,140 CHF for the second place, and 570 CHF for the third place. And some key deadlines are listed here. For example, you should the registration deadline is December 15, 2025, and the development phase deadline, which aim to determine the top 5 teams, is February 1st, 2025. The final material submission deadline is February 10, 2025, and the final ranking announcement is February 15, 2025. If you have any other questions, you can also contact us by these 2 emails. Thank you for your listening, and you are welcome to ask any questions. Thank you.
Thank you very much, Ocean and colleagues. Yeah, that's a wonderful presentation. Thank you very much. Maybe while we wait for some questions, Boshan, WiFo based models. Can you tell us a little bit more about it? Like, how is it trained, or what data sets are used to pre-train it right now? Can you please describe the base model a little bit more?
The
WiFo base, yeah.
Can you repeat the question? Or
The
can
WiFo,
Professor? Okay.
Yeah,
WiFo base.
the base model. Yeah.
Can you repeat the question?
Sure. I will put it here. The WiFo base model. Can you describe the WiFo base model?
Professor Tsai, can you understand this question? Okay. You mean the detail of the base model of the WiFo?
Yeah.
Oh, okay. Yes. For WiFo, we have we have 5 versions. Including the tiny, small, the base, large, and the base, the different, they have different parameters, because they have different layers of the encoder and the decoders, and their structure is their overall structure is the same. It's all consists of these 4 parts, and the WiFo based model is just a medium size of the WiFo family. Can you understand?
Yeah, thank you very much. The next question is the submission format. Can you describe a little bit about the submission format?
Okay. In fact, the submission format is it's a bit complex, and you can refer firstly you can refer to our website for more details of the submission format. And another way is that we have provided the baselines, and yes, this link. You can enter this link, and in this baselines we have provided the expected submission format. Due to the time limits, I can't explain this submission format in detail.
You mentioned the line of sight and non-line of sight data. So is the data set contains both line of sight and non-line of sight data, and how is it balanced? The data set is having both line of sight and non-line of sight, and how much of both is it balanced between the two equal? Mm-hmm.
Okay. We have the same number of lost data and unlost data. That number is same.
Okay. And I think you don't allow external data for fine tuning, but you allow external data for pre-training. Why?
Yes.
Why?
Yes.
Yeah, why?
Yes, we allow the participants to further pre-train the WiFo base, because we think it's more difficult for pre-training rather than the fine-tuning. And is and if and our competition aims to evaluate the fine-tuning performance of the WiFo base on these three tasks. And if they use external data, it's not fair. It may greatly impact the fine-tuning performance in our testing data sets. Okay, and someone asks that is there compute GPU available? Sorry, we don't provide available GPU for fine-tuning or retraining.
No problem. Actually, ITU can provide compute GPU. If any of the participants need compute GPU for fine-tuning or pre-training, they can contact us and Chai. We will provide compute GPUs. No problem. Maybe the downstream tasks itself. What are the downstream tasks? The channel estimation, and I think you mentioned maybe let me see. So scenario classification, and in that you have channel estimation and wireless localization. So there are three. These are the three downstream tasks, or are there other downstream tasks? What are the downstream tasks?
These three tasks these three tasks are downstream tasks. Our WiFo is originally designed for the channel prediction or channel reconstruction, and in this task we aim to empower enable the WiFo to empower the downstream task. The downstream task is defined as the task that's input is CSI and the output is other features. And in this challenge, we select the channel estimation, loss and loss classification, and the version wireless localization.
Okay. What is the data set format? And can you tell us the data schema? Is it, I think it is structured data with CSI values and location maybe?
Yeah.
Yes.
Yes, we provide the dataset in the MAT format. MAT. This format for MATLAB. And we provide the data volume. You can check this link for further details. And for each task, we provide a different type of data. For example, for channel estimation, we provide the CSI as a pilot position, and we also provide the label that is a complete CSI. And for the second task, we provide the input data is CSI, and the label is the scenario labels. And for the task 3, the input is we provide the input data that is vision RGB images and the CSI, and the label is the label is the localization results.
Okay, thank you. You mentioned the data set is in MATLAB format. So is it simulated data, or is it real data, testing data, or simulated data?
Yes, it is. Although whether it is simulated data is it's not determined by their by the format, but in fact it's the simulated data by simulation or retracing and other software.
Basically, sorry for interrupting. So basically, we use Siona RT to produce the channel data, and the LSIM to produce the RGB data, right, Bertrand?
Yes. For the task 3 is right.
Yeah. So all the data are simulated.
Yes.
Channel and airstream. Okay, thank you, Dr. Thai. I think that makes sense. How many base stations, if you can tell, how many base stations, how many access points, or how many? Yeah, how many?
Yes. Only one base station in this dataset, and we consider the single user in each simulation.
But the scenarios can be very different. So the distribution of the data can be very can change a lot. So yeah, but it's still like single base station to single UE data.
Yes, for each link is that.
Yeah.
Do you cover mobility? Is the UE moving, or is it stationary?
Yes.
Yes,
the UE moves with different speeds in the simulation.
Yes. The mobility is important for such a channel estimation. It determines the variation in the time domain.
I see. Okay. So can the participant use Shona to generate new data for maybe pre-training? Can they generate new data and use it for pre-training? Is it possible?
Yes, it's allowed. They can use any simulation data or real-world measurement data for further pre-training the WiFo. But this pre-training should be reported in the submission document, the submission materials in the final phase. in the phase 2, the test phase.
Okay, thank you. Thank you. Okay, maybe do you plan to publish papers based on the submissions? Maybe can the winners join you? I think it'll be an honor and a pleasure for the winners to join Dr. Tai and yourself as co-authors. So do you plan to publish papers based on the submissions?
We will not publish papers, and the participants can publish papers based on their submissions, and we can co-author if we have some communication and
contributions.
If we have truly contributions.
Okay. Okay. Maybe the evaluation scores. Why do you select these evaluation scores? I think you have different evaluation scores. So can you describe the evaluation score for each task and explain why that score is selected or score is used? Yeah.
Okay. Yes. Firstly, we have metric for we have different metric for the 3 tasks, and based on the metric we build the score, and the score is the score need to make sure you see, Professor.
Yeah. So because we have 3 different tasks, and so the first task is basically regression, but the error should be the relative error is very important compared to the for example, the power of the channel. So we use NMSE to score this task, and the second task is basically classification. So we use the classical scores listed here. And for the third task, because it's localization, so we care about the absolute error of the localization. It's not relative error. So MAE is used. That's our motivation. So yeah. So it's task.
Yes. A professor has explained the selection of the score and the metric, and additionally, I want to say that the score is need to make sure that the range is 0 to 1 for normalization. That's all.
Thank you. Can you describe the practical impacts of this challenge? For example, what is learned from this challenge? Maybe we can have some scheduler mechanisms, or maybe there are some new algorithms, or maybe how to integrate AI. What are the practical learning?
Okay. I think this challenge is a preliminary attempt to adapt a wireless foundation model to the downstream wireless tasks, and we aim to explore how the AI can empower the wireless systems. For example, for channel estimation, it is very important, or it's the main way to acquire the CSI, and CSI is very important in our wireless system design. And the loss and loss scenario classification is also very important in wireless systems. For example, they can get the communication strategies selection or some wireless localization algorithms. And for the third task, the vision-aided wireless localization, we can explore the additional sensing modality to aid our localization. It is very meaningful, I think.
Thank you. Maybe what are the future tasks? Maybe the more downstream tasks, maybe such as beamforming or beam optimization or this kind of tasks. Do you plan to add such tasks in future? What is the future research? Future research, yeah.
Okay. Yes, yes, we plan to research in the future for more downstream tasks, including beamforming or pre-coding uh, or other tasks. Considering that the CSI is play a vital role in the wireless systems, and there are so many tasks which is where the input is a CSI, and we can use we can utilize the WiFo to empower these tasks, and there are truly so many tasks to explore via WiFo.
Yeah, I think Bertrand, you already researched a lot of other downstream tasks.
Yeah,
For example,
yes.
channel feedback detection and crossband channel prediction, beam prediction, and so on. So yeah, many tasks, and yeah, you want to use these. Yeah.
Yes, and more tasks we have not explored.
Yeah, thank you. It is very exciting research. Yeah. Maybe the configuration, the UE configuration, including the antenna configuration. What is used in this data set? I think you have in the slide you mentioned some configurations for the UE, but what is the configuration is used in this data set? And for the other downstream tasks that Dr. Tai mentioned, including beam alignment, beam optimization, selection, this kind of task, what is the change? What is augmented in the data set for this new downstream task?
Okay. During the pre-training, we use a data set that we use a heterogeneous data set that configure that consists of different antenna configurations, and for this downstream fine-tuning tasks, the antenna configuration is fixed, and the detail configuration you can refer our dataset link, and in the future, we may explore more configurations for pre-training to we may explore a bigger dataset with more configurations to empower the pre-training of wireless foundation models.
Question: did you use what kind of antenna panel did you use, and how many antenna elements in the UE or
I'm not sure.
Okay.
I'm not sure.
Okay. But but in the future, because now all the data are basically simulation dominated. So in the future, we plan to augment this data by using real measurements. So combining the advantages of simulation and measurement, because simulation we can produce a lot of data, but the quality is limited. But with measurement, we can have very high quality data, but the volume somehow is limited. So we combine both simulation and measurement, we can produce very high volume and high quality data, and this will enhance the ability and the generalization of our WiFo model furthermore. So it's more practical in the future. Yeah.
Thank you. Thank you. Can we publish your slides? It will help the participants to understand the challenge better.
Of course, of course.
Mm. Maybe the baseline results. What are the baseline results? Are there some reference papers that from yourself or Dr. Tai, which our participants can refer to?
I think they can they can the the detailed results I need to check and they can refer this this link and the reference papers the mainly reference papers is a paper of WiFo this paper yes and for more reference papers you can refer to our website. There are lists of papers.
Is there a specific frequency band used for this simulation?
Yes, it's the frequency band is a sub-6 gigahertz frequency band.
Sub-6. Okay. Okay. Thank you. Yeah, I think we don't have any other questions. We are very happy to host Dr. Tai and the team for the challenge. Thank you for patiently answering all the questions. Thank you very much. Staying back to you. Yeah, thank you.
Thank you.
Thank you, colleagues. Thank you, Vishnu and colleagues, for your Q&A session and all the participation. Thank you so much for your contribution during the whole talk. Now I'd like to also thank everyone who participated in this webinar. The challenge has already been, the challenge link has already been put it on the video wall, and it's also available for registration and participation. You can now work on the solutions and of course submit the results on the portal. Several prizes, as mentioned by Boshun, and certificates, of course, will be handed out to the winners of the challenge. And from ITU side, CPU and GPU will be provided based on needs, so you can absolutely contact us and also Boshun and Professor Tsai for any information and assistance. As we mentioned previously, the slides will be published on the website, which is also linked to the challenge website itself, and it has already been put on the video wall. So if you want, you can check it maybe a day, maybe tomorrow or the day after. You will see the slides be available online. And thank you so much, Boshun and Professor Tsai, for all your engagement. We have more sessions in the future. Please check the AI for Good program page for more details, and we look forward to see you in the future. Thank you so much for joining. See you next time.
Thank you. See you.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learnt something new innovative and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.